Hello everyone. Today I'll be talking about our project Deep RL for RGB-D SLAM. This work implements a custom RGB-D keyframe of postgraph SLAM pipeline on the TUM Pioneer SLAM 2 sequence. The system uses OR-based visual odometry, motion-based keyframe selection, loop closure detection, and postgraph optimization to recover a consistent trajectory. A major challenge is manually tuning several interacting hyperparameters controlling keyframe creation and loop closure robustness. Because these choices strongly affect accuracy and graph sparsity, we embed the pipelines inside a reinforcement learning framework. A reinforced policy automatically tunes its six key thresholds to reduce trajectory error while maintaining a compact post graph. So, what is SLAM? SLAM estimates both the camera trajectory and the consistent map from sensor data. Here we use RGB-D input, which provides per pixel depth and just metric scale. Our pipeline is a feature-based post-graph system, which uses ORB plus PNP for frame-to-frame motion, motion thresholding for keyframes, descriptor-based loop closure proposals verified with PNP plus ransack, and global optimization to enforce consistency. So here is a brief overview of our dataset. The pipeline begins with visual odometry, which includes ORB features, descriptor matching, and PNP ransack for relative pose. Keyframes are selected using translation, rotation, and frame cap thresholds. Loop closures are identified through descriptor similarity and verified via PNP. All keyframes and constraints from a pose graph, which we optimize to produce the final trajectory. I should talk about some of the critical SLAM hyperparameters. These include the ORB feature count, ransack thresholds, minimum inliers for visual odometry, and translation rotational thresholds, which we need to optimize. So why is hyperparameter optimization necessary? SLAM hyperparameters are highly sensitive, which means that small changes can dramatically alter keyframe frequency or loop closure reliability. Because we must jointly minimize AT while preventing overly dense or unstable post graphs, tuning becomes a multi-objective problem. And RL provides a scalable way to search this space automatically. So here is how we integrate SLAM into our entire pipeline. We wrap the SLAM system in an RL environment. For each episode, the agent proposes six hyperparameters. A dataset segment is selected and the full SLAM pipeline is executed. And the environment returns accuracy and sparsity metrics, which form the reward. This creates a one-step RL task for learning effective threshold combinations.
Moving on to algorithm and policy architecture, we use the reinforced policy gradient method. The policy is a small MLP with two 64-unit layers, producing six continuous values. Actions are sampled from a Gaussian distribution and squashed with tan. Each episode provides a single reward, enabling a simple and fast update. The approach is computationally feasible while still exploring the full hyperparameter space. The key reward prioritizes a low ATE RMSE on the optimized keyframe trajectory, with penalties for high keyframe and loop closure density. This encourages accurate yet sparse postgraph structures. Here is our RL training setup and environment behavior. Each episode evaluates one contiguous segment which is greater than 200 frames. The observation contains basic segment descriptors. Learning is driven almost entirely by reward. Training typically runs 50 to 100 episodes and the best reward configuration is saved. The environment is deterministic, making training stable and reproducible. Now, here's the effect of deep RL on a SLAM. RL consistently selects larger motion thresholds and longer frame gaps, producing far fewer keyframes than the baseline. Loop closures also become more selective, yielding a much cleaner and better conditioned post graph. This reduction in redundancy improves both runtime and optimization stability. The RL optimized configuration improves ATE RMSE from baseline's 0.46 to 0.34 while using less than half as many keyframes. Raw VO does not change. Gains arise from better keyframe placement and strict loop closure validation. Trajectory plots show visibly tighter alignment with ground truth, especially in revisited areas. The RL postgraph is sparser and contains only high confidence loop closure, making SE3 optimization more stable. Keyframe align more closely with true motion rather than arbitrary spacing rules. The visualization and short video illustrate how VO inliners and keyframe decisions and loop closures occur along the trajectory.